Okay, we're going to solve a two-dimensional projectile motion problem. This is chapter 3, number 34. It's about during the Apollo 14 mission, astronaut Alan Shepard hit a golf ball with a makeshift golf club, and we're asked to find out how long the ball would be in flight. Of course, not in the air, no air on the moon. How far did it travel? And we are told that the acceleration on the surface of the moon is 1/6 of g, so that's 1/6 of 9.8 meters per second squared. And we are told to assume that he hit it with a speed of 25 meters per second at an angle above the horizontal of 30 degrees. And the question is, how long was it in flight and how far did it go? So notice that what I've done is taken the verbal description of the problem and taken those sentences and rewritten them as mathematical expressions giving us some of those parameters. So this is two-dimensional projectile motion. The ball is traveling up as well as horizontally, but we can set out our parameters of kinematic motion in two dimensions. So for the horizontal motion, I'm going to write out what we're interested in is how far it goes. That's one we don't know yet. The initial x velocity, the final x velocity, the acceleration, the time we also don't know. Now for projectile motion, the only thing acting on it is gravity, which acts only in the vertical direction, so there's zero acceleration in the horizontal direction. The initial velocity in the horizontal direction we can get from the description. We are told that the magnitude of the initial velocity is 25 meters per second, and it's at an angle theta of 30 degrees above the horizontal, and so we can immediately get the two components of the initial velocity in the horizontal and vertical direction. Vix is Vi cosine 30, and Viy is Vi sine 30. So we can go ahead and calculate what those values are. Vi is 25 times cosine of 30 times 25 gives us 21.65, 21.7 meters per second in the horizontal direction. So that's about as far as we can go with the vertical motion. With the horizontal motion. With the vertical motion, we're going to write out the parameters for the vertical component of the motion. So there's the vertical displacement, the initial and final vertical components, the velocity, the acceleration, and the time. The time is the same as what we had before. What's the vertical displacement of the motion? He hits it off the ground and it lands back on the ground. We're interested in this entire flight. It's launching here at Vi, and it ends up landing. So the vertical displacement is 0. The initial y velocity, we already said, is Vi sine 30. Sine of 30 is 0.5 times 25 gives me 12.5 meters per second for the initial vertical component of the velocity. From symmetry, since I end up at the same height, I know that my final vertical velocity down is equal to the initial vertical velocity up, so that's minus 12.5 meters per second. And the acceleration is 1/6 g, which is 9.8 divided by 6, or 1.6 meters per second squared. So in the vertical motion, I actually know everything except time. So I'm just going to figure out one of my kinematic equations to solve for time. The easiest one to do that with is Vf equals Vi plus At. The other one has a t squared. I don't want to mess with that. So Vf equals Vi plus At. That gives me minus 12.5 equals 12.5 and I should have put a minus sign up here for the vertical acceleration because it's downwards. The acceleration is downwards, and we defined the initial velocity, which is upwards, as a positive number, so this has to have the opposite sign, minus 1.6 times t. That then gives us 1.6 t equals 25, or t equals 25 over 1.6, which is 15.6 seconds. So that's how long it's in flight. Then I can use that piece of information with my horizontal motion to get the distance that it travels. So I have, for the horizontal motion, x equals vi t plus 1/2 at squared, but the x component of the acceleration is 0, so I just have x equals 21.7 meters per second times 15.6 seconds. So I just take that times 21.7, and that gives me 339 meters, which is a pretty good drive. Of course, he's on the moon. So, by the way, had I used y equals vit plus 1/2 at squared up here for the y motion and to calculate the time, it would have worked out okay because y is 0. In general, if you're solving this equation for time, you only want to use it if either vi or y is 0. Now you can use it to solve for vi or a or y regardless, but if you're trying to invert it and solve for the time, you don't want to have all three terms be non-zero because of that t squared there. If that does turn out to be the case, what you want to do is get vf from one of the other equations and then use this equation to get the time. But in this case, since y is 0, that would have just given us 0 equals vit plus 1/2 at squared, and then we could have canceled out one of the t's and we would have ended up with the same result.